Hello and welcome to Lab 2, Map Interpretation. What's neat about this lab is we're going to learn how to interpret topographic maps, both physical paper maps, and we're going to utilize some different geotechnologies such as Google Earth Pro to really learn more about how we can observe the landscape in really a bunch of different ways. I think it's interesting because a lot of people assume that traditional paper maps are out of date, but the reality is they're still very impactful for our discipline. We still utilize them from a historical aspect, a cultural aspect, and we still use it to just collect overall data for hiking and traversing the landscape. We can also utilize that topographic data and overlay it on 3D digital elevation models. So there's a lot to be said with that. Again, don't forget to review the learning objectives, what we will be accomplishing, the introduction, and well, let's start with lab number 2. So lab number 2 introduces cartography. Cartography is the science of map making, combining technical information, design, aesthetics, cartography, all to build really a virtual or paper landscape that reflects the real world. It's very important for us to understand cartography, not just from a geographer's standpoint, but from your standpoint as someone who is into video games and to digital technology. We'd have to design believable landscapes for video games, and who can do that no better than a cartographer. So what ends up happening is we introduce the values and the premise of cartography, that cartography has, to be able to make a map is a lot of power, which kind of seems weird, but as a map maker, we can control so many different attributes and emotions and feelings because we're portraying information, we're portraying data, and sometimes the person who's making the map might have a motive of some sort and will want to present data a little bit differently. So, when we learn more about maps, we learn more to dissect them, to understand them, to see the credibility, where the information came from, what it's truly trying to represent. So there's a lot of really interesting aspects of that, aside from just paper maps, but everything from there to video game design is really, really involved in the ideas of this. Now, moving forward to the next page, Part A, map projections. So the first thing that needs to be observed is that at the end of the day, the Earth is no oblate spheroid, it's round. Think of it like an orange. There's no way for you to peel an orange so the peel is perfectly square. But how come our maps are square? Well, that's because of what we call projection. Now, most projections transfer most of the imagery from the globe into some developable surface. The three that we use are planar, conic, or cylindrical. So the way that's done is essentially like wrapping a piece of paper around the globe. If we wrap a piece of paper around the globe going this way, it would represent a cylinder. If we wrap it at an angle, it would represent a cone or conic, and planar would just be on one piece or one surface. So we learn to identify each one and how that works. Now, moving on to the next page, we see an example of each one of these projections: cylindrical, conic, and planar. So down below you'll see this QR code and the website to check out why all world maps are wrong. It's really, really a great short video. It's only 6 minutes. I highly suggest it because I just think it's a really interesting perspective on cartography or map making. So now we move into map distortion and social injustice. So again, like I mentioned, there's a lot of power behind those that can create maps. So let's move on to that page. So it says one of the main factors to consider is map distortion. All maps have some form of distortion because it is impossible to transform the three-dimensional Earth onto a flat surface without causing errors. There are 4 primary types of distortion: area, shape, distance, and direction. Each of the projections found in figure 2.1, which is shown above, creates some form of distortion when taking from a globe to a map. So what we see below, question number 1 specifically asks you to look at the 3 types of projections in 2.1 and decide which projection would be best to make a map of a great circle, a small circle, or perhaps a map of a continent. Question number 2 asks you to kind of look more at the social injustice of maps. So it says refer to figure 2.2, which is this map down here. And then it asks you a couple questions about that map, such as what are your very first observations of this map? And also take a closer look at the map. What more can you observe from that map? So you'll go ahead and write those answers in there, and let's move on to the next piece. Now, a danger with map projections is that the map may enlarge certain countries, which can make them seem more powerful or intimidating. This concept is not new. It's known as the power of representation and the representation of power. So as an example of this, observe the map, figure 2.3. It says map of Africa in reference to 18 countries and land masses, and answer questions 3 and 4 as it pertains to your observations of this map. Question 4 has you reference that, and as well as an earlier image in 2.1. So again, the purpose of this is, when we look at different maps that are available, whether it be world maps in particular, there are different distortions, shapes and sizes. Some countries can be smaller or larger. They have to decide where to gain and lose, but sometimes it can be done vindictively, or it can be done on purpose to make certain areas look small or large. And I think that this is a great representation. Figure 2.3, map of Africa in reference to 18 countries and land masses, really paints a very prominent and an impactful image of just the sheer size of Africa. So let's move forward. Now, here we can look, sorry, I'll mention this too. Check it out. Take your cell phone or click the link with that QR code. It'll take you to a comparative real size of countries diagram. I think it's a great way to just, reflect and to observe different places. So if you really enjoyed looking at that photo of Africa on the previous page, this is a great way to then compare any place on the globe. And I think it's a great example of that, of the true size of website. Now, part B is looking at map elements. Let's begin talking about maps. Now, it's very important to be able to learn how to interpret the map elements, meaning the context that is designed within the map, because the map itself has a tremendous amount of data, but there's a lot of other elements that can be found on the map that are equally as important as the data on the map itself. An example of that would be the map scale. The Earth's surface has over 500 million square kilometers, and any picture or map of the Earth you can easily carry in your pocket will not be able to represent all of that data. So we need to find a way to create some form of scale, to represent that sheer size. Now, there's two ways that we're going to, there's several, but the two that we're going to work with first are fractional and representative fractional scale itself. So when looking down on the next page, I'll scroll there, you're going to learn the verbal scale versus the graphic scale. And then within the graphic scale, you're going to be able to distinguish fractional and verbal back and forth. So it says for verbal scale, some maps, especially older ones, use a verbal description. For an example, it is common to see it written out as 1 centimeter represents 1 kilometer on this map, or something like that. Now, a graphic scale literally takes that written sentence and represents it as a diagram. So as an example, we can see as a graphic scale, the fractional representation is 1 to 63,360, or a 1 to 1, or a graphic bar graph or bar scale itself. So we're able to observe these things. So question 5 is having you look at the math of breaking this down. So it says, now that you understand the basics of map scale, write in the missing scales in figure 2.5. Note that the American units are shown for the top table and metric units are on the second half. So you'll be able to get this information from this page, page 7, as well as page 6. So question 5 does have you fill in both of these graphs. As you can see, there are 8 open boxes that you must fill in. All right, so then moving forward to page 8 is distance conversions. Map conversions and math conversions and all kinds of conversions can be very, very challenging. The United States, Liberia, and just those to mention, have not adopted the metric system yet as its primary form of measurement. We still use imperial in different units, and it's a whole disaster. So we need to learn how do we, find that conversion rate. As an example, how many miles are in a kilometer, or how many feet are in a kilometer, and vice versa, back and forth. So there's some great information here. I'm going to scroll to the last page, all the way to the end. You'll notice on the last page of this lab, there is an appendix, distance units of measurements. This will be very helpful to complete page 8. Okay, so you have that as a reference for your scale. I'm going to scroll on back to page 8, and you'll be able to then fill that out. As you can see, refer to appendix 2.1 to get that data. So why is this important? Well, because when we look at just overall maps and data, some places will use metric, some will use other units, and so we need to have some form of uniform understanding, or that language of distance. Otherwise, the map isn't going to make sense, because we can find there's many different types of maps that have different types of scales, which can then produce false information. You know, I guess a silly example of that would be is if you're trying to buy fabric and you're going to make something with that fabric, a shirt maybe. Well, are you going to be using inches or centimeters? Well, if you have your fabric cut in centimeters but you needed inches, you're not going to have enough, and vice versa. So it's really important for us to understand the difference in conversions and scale. Now, the next step are going to be contour lines. Now, contour lines are the actual lines that are drawn on the map, and they're very, very important. They actually interpret and represent the topography, or the landscape. So it's very challenging for us to view a flat map and try to visualize it in some form of third dimension. And contour lines have that availability for us to observe that. That being said, before I move forward, just in case I forget, there are additional videos shared within this, down below within the description, that show how to interpret contour lines both on a map and looking at it in a 3D environment using Google Earth Pro. So again, we're going to skip to this next page, page number 9, and I think this is an excellent example of how to represent topo contour lines, but in a more realistic fashion. So in this, I'm using a 3-tiered cake as an example: a chocolate, a vanilla, and a berry on top. So as you can see, when I put my cake together, it's a little off to the right hand side, but you can easily distinguish that there are 3 prominent layers. Now, the image to the right of that would be as if I was looking down at the cake that I've made. Well, that's what topographic maps are. It's the aerial view of the landscape. So I can see that anything here, here's my mouse, this all represents the chocolate layer, this all represents the vanilla, and this is the berry. What's also interesting to point out is that, you know, as a cake, I know that the right-hand side, see how close these lines are together? That means that it's very steep on that side, versus on the left-hand side, see how much space is between the contour lines? That means it's not as steep. So we find that the closer the contour lines are together, the steeper the topography will be. So question 7 asks you to observe the cake and to really just write your observations and your interpretations. Then it has you apply some values or elevations to these cakes and then these layers themselves, and you'll go ahead and answer parts A, B, and C. Now, topographic maps show lines for selected elevations. Otherwise, the map would be just really too confusing to read if it had one line for every piece of element of elevation. It would just be too much. Now, the elevation difference between contour lines is known as the contour interval. So if a topographic map has a 10-foot interval, that means each line has a value of 10, meaning it goes 0, 10, 20, 30, 40, and so on and so forth. So question 8 has you refer to the lines that you've drawn on figure 2.6, and it's asking you to identify what would be the contour interval of this map, this guy right here. Now, moving on to this next page, guided practice, drawing isolines. So this video here is one that I made, teaching you how to do this activity that you're going to see next. So I call it connect the dots. Now remember, contour lines are elevation lines that are constant. They never cross, they never change, they don't disappear, they don't go up or down. They remain the same as they're drawn all the way around. So below you will find an image that consists of only elevation points, and you need to connect the dots. So let me scroll to that page so we can speak to it. So this is a map, but it's just elevation points. Our job is to connect the dots, connect like elevations, and if the elevation is not there, we have to add it in. So as you can see, as an example, here's my mouse. There's a 40 and a 40, and there's no other 40s, but I can see that 40 would be between 38 and 45, so I'd be able to add my line in there. So your job is to draw an entire topographic map based off of the instructions found up here. Excuse me. Okay. Again, there's a video there that I shared above in the lab with the QR code, where I essentially do one very similar to this. I show you step by step on how to complete it. And I think it's really neat. It's really fun to be able to see how these topographic maps are made step by step. So now that you've completed your overall topographic map using that data, let's talk about some of the relief features that can be observed on topographic maps. So relief features are influenced by the drainage of the area. Running water works upon the surface of the ground, eroding and transporting the softer material and leaving the terrain with characteristic valleys and ridge patterns. So question 11 has you reference the next image, and it says observing the patterns on the map. You see that there are 3 areas on the map where all the contours make a V shape. Well, when contours make a V shape, that implies to us that the tip of the V is actually pointing upstream. So it says to use a blue colored pencil to draw each of the 3 rivers and to include the arrow showing the direction in which the water is flowing. Question 12 says, on top of this mountain, you're to draw a smaller contour line inside with a brown pencil. It is to replicate the bottom of a lake. Now we know the lake must be deeper than a 180-foot contour, so along that 180-foot contour, you're going to draw little hasher marks, which is seen here in figure 2.9. And then you'll go ahead and complete the question itself and part A. Now, topographic profiles. So far here, when looking at Three Rivers Mountain, we're looking from above down. When we talked earlier about contour lines, we used the example of the 3-layered cake, and we looked at the cake going, this way and going this way. Well, how do we draw a profile, which means that we're looking at the environment going like this, for we're down and looking at it? Well, topographic profiles is the way that it's done. A common way to understand what the topography really represents is to construct a topographic profile. So let's move to this next page. Now, a topographic profile, in other words, is when you would essentially slice through a portion of a cake, pull that half away, and look at it from the side. And we're able to see all the different layers. So as we can see here for question number 13, a topographic profile appears if you select the cycling options on Google Maps. So go ahead and take a photo of that QR code, follow the directions, and it will walk you through that process. Now, before completing a topographic profile, you must identify a line of interest between 2 more points. This will be called the transect. So what this next part is going to have you do, I'm going to skip to that page, it gives you the step-by-step, is that utilizing this map that's been drawn here, we've drawn our line. We're going to follow the steps on how we collect the data that's been observed on this map, and then we're going to be able to draw, here's my mouse down here, we're going to draw our profile as if we were looking outwards. The way that I always explain this to my classes is that if this diagram here, this map, were to represent a cake, we're on some cake TV show and we want to make this very special map, how many cake layers would we need? Well, I would need, the bottom one, so 1, 2, 3, 4, 5, 6. And it'd be at least six layers in height. So you would need to then interpret that to carve it out and to create that side view, that profile. Again, if you need additional help, there is a video found below within the description of this video posted that gives you an example of how I would do something like this using a different type of map. Right? And that'll be a lot of help. moving forward, we have additional questions, questions 16 through 19, that have you interpret that map. What's the highest elevation possible? What is the lowest possible elevation? What is the elevation for points A and for point B? And then there's a big think about it. These think about it's are really important in the labs because there isn't essentially a writing prompt for you, but it's trying to give you an idea to kind of relate it into real world experiences. And these are great topics to find on exams because what you're doing is you're taking everything you've learned and putting it into some thought. So, this is talking about gradient, which is rise over run. It's slope. So is it really steep or is it less steep? What type of gradient are we looking at? And so that's a really great part to evaluate. So let's look at part C. Part C is going to have you interpret a topographic map. So it says by using the previously learned information, you'll now be able to observe and interpret basic information on topographic maps. This activity will introduce some content from Lab 1 when dealing with latitude, longitude, even township and range. But ideally, it's putting it all together. So the first thing we have is a guided practice video. And it says to watch this video by me for a quick introduction to the key features of topographic maps and tips on how to interpret them. I know it's a long video because I go through a lot of different visualization. I use 3D imagery and I overlay it with topographic maps so you can see how, as a geographer, do we look at a flat map and visualize it in 3D, and we look at all the different attributes and importance of topographic maps themselves. This other check it out is really interesting. That it introduces some of the map symbols that can be observed. And then we can see that there's another one moving into step 1, which is the map collar. Now what's interesting about this activity is that it is designed for really any topographic map. So make sure that you're using the appropriate map that has been assigned in your lab because you never know which one you might get. And I know that at least for myself, I update it every semester, so there's different maps that are out there. So make sure that you're paying attention to the context. So step 1, reading the map collar. The map collar is the data that's wrapped around the perimeter of the map. It's not even the map itself. It's on the white part around it. And this little video will help you interpret some of that information. So we can see that questions 20 and 21 are going to really have you dive into just your observations. What are you learning about the map by just looking at it? Then if I move on to the next page, we have questions 22 through 28 that just have you, again, pick out these different pieces. What is the contour interval? What is the scale? What is the magnetic declination? What is the western edge or the northeastern edge? So it's having you really just scan the lab and look at the different attributes and elements that can be found. Now, that's just observation. Now for step 2, we need to read it and interpret it. So step 2 really has you look at the context and the details inside the map. So question 29, it says the following questions are referencing the Public Land Survey. Identify all the townships, identify all the ranges, identify the section and township and range for the center of the map and the extreme northeast corner of the map. So it's really having you look at the map itself. Question 30 is after referencing the contour lines of the map, it's having you a short answer. It's saying, what do you notice about these features? What are the things that you observe? Is this a flat map? Does it look like it's very mountainous? Is it by the beach? What are the things that you're interpreting from the data that's been presented? Now to wrap up part C, we see question 31 asks you to reference the latitude and the longitude. So if you don't remember the differences between those, be sure to reference your lab 1 and the videos that are found there. So it's asking you to identify what is the northern latitude and the southern latitude and the total minutes, the distance in minutes between those two. It's also asking you to identify the eastern longitude, the western longitude, and the total distance between those in minutes. And then questions C and D, as part of that, ask you to really interpret that information. What is the minute series of this map? Using your critical thinking skills, what is the shape of this map? Why is it not a perfect square? And explain why. So then moving into part D, the surveying activity. This is something really fun. We've learned how to interpret that data. We've learned how to draw out a map, but how do we actually get that data from the field and turn it into a map? And that's what Part D is about. So land surveying is the art and science of mapping and measuring the landscape. Although the details are very specific, the production of mapping space is relatively easy. So throughout this lab, you have learned how to observe and interpret data on maps. And in this particular activity, you will learn the basics of survey data collection and how to take that data and place it onto a map. So the first step of surveying is to know the language. And so what we have here first is a list of vocabulary that has been applied to an image below. So we can see that some of the terms that we utilize in the field, such as backsight, foresight, height of instrument, elevation, bearing, and so on and so forth. So we can see there's a definition, the backsight. A backsight is a point of a known elevation and location. They're often observed as a small brass marker that have a little data on it, and that gives us what's considered in 3D imagery an XYZ coordinate, a latitude, a longitude, and an elevation. So then we can see we have our foresight, which is an unknown location, the height of the instrument, and perhaps you've seen these guys out in the field before. So we've got all kinds of this really great data. We also have information such as the elevation and bearing. So this little diagram here that I've drawn is representing how do these terms apply to when getting data and when we're surveying out in the field, and then what are the formulas needed to solve. So be sure to work through this very slowly and carefully. So then we move a little bit farther about what is being observed. So that little device, they're looking through it and they're looking at the survey marker, and they're looking also at a ruler, a really large measuring stick that has different attributes to it. So this teaches you about that. So it's like a sight, like as if you're looking through either a BB gun or something like that. It has a little sight that you're looking through, and it has 3 lines. It has stadia A and B in the horizontal plane. So these instructions take you step by step on what this means. Why is this important? Which brings us down to this. Check it out. Using an auto level in the field. So this portion of the lab might have you wondering what this even looks like in the real world. So check out this video. It's from the Illinois Surveys Association, and they're going to show you how the device works. And then we're going to be able to then plug that information into this table, figure 2.15. So our job here is to fill it in. We have some data that's been provided, and it's our job to solve it. So again, be sure to check out the step-by-step video that I have shared within this description within the YouTube channel for a little bit more help. But your task at hand is to solve all the distances and the elevations in these remaining 4, 5, 6, 7 boxes. So once you've done that, we're going to move on to this next piece. Oh, there's the link to the video on how to create a contour map. We're going to use that data to make a map. So here's data already been presented. What you're going to need is to cut out a protractor and this ruler. These are not to scale. I know that. Don't use a real one. Use these ones. Cut them out because these are designed specifically to work on our map. And then we're going to be able to speak to our map here. This is the map that we're going to use. Again, like I said, there is a video shared above that takes you step by step on how to make a map. And what you're going to do is by utilizing this point, you're going to take that data, measure the bearing, plot the distance, put a dot, and you're going to create your own contour line on a blank map, which is kind of cool. I think it's a great way to really bring this all together. Now, then, moving to our last part, this is called the Google Earth Pro activity. Google Earth Pro is free, and it's a wonderful resource. You probably have played with Google Earth at one point, but this is just really, really, really interesting because we're able to utilize tools that were not available before for free, such as the time-lapse tool. So we can actually look at historic imagery. So this one in particular, it says once you've downloaded and opened up Google Earth Pro, you're going to search for a place called Lake Piru. Once there, you're going to zoom in so the lake fills the screen of the window. And then you're going to follow these steps throughout that process. It's going to ask you and teach you how to draw the perimeter around the lake. And then you're going to be able to learn how, by drawing your little points, what is the distance around that lake, and then you're going to do it again at a different point in history, and to see if there's been any change in the total, circumference or perimeter of that lake. And the reason that I have included this assignment is because I think it really introduces you to Google Earth Pro, that you're going to be able to utilize these skills for other things. Maybe you want to plot hiking trails or distances or traveling, or you want to make a map or see things in 3D. I mean, you can visit anywhere you want in the world in Google Earth Pro and observe it in a three-dimensional rendered video game design, and it's really, really remarkable. So as I scroll down, I have some visual representation of how you'll work through that, and then you'll be able to complete questions all the way through 39. Again, the last page is your appendix. So I know there's been a lot said here. It's kind of, I think this is a fun lab. It's kind of a two-parter, but I'm certain you certainly will have plenty of time to complete it. Again, what we're going to be learning now is we've taken the ideas of latitude and longitude, and now we're overlaying that into how do we interpret that? How do we observe it? So we look at topographic maps. We can look at Google Earth. We can look at the items on these, such as contour lines and these values to observe our landscape. I would have to say the hardest part is going to be, when you're learning how to collect the data to make your map. So be sure to read those directions and to watch any supplemental videos that will be provided for additional help. Again, if you need anything else, be sure to comment below. Don't forget to like, subscribe, and we'll see you soon on your next